Alright, so what we should have found here in example number 2 here, that when we put this function here into our calculator, what we should get there is that x is approximately equal to 7.74. Okay? So you guys want to put that in for x and see if it works, and what we should find is that they are approximately equal to one another. Okay? So the next two examples that we're going to look at, they are word problems, and here I have given you a wonderful way to write, I guess, any of the word problems, especially that we're going to be looking at in this section. So here, in general, what we can say is that we have our final quantity that we're given in the question is equal to the initial quantity times the change factor to the exponent of the number of changes, okay? So it's probably right now, it's probably like, what on earth are you talking about? Let's look at some examples of what this is going to look like, okay? So moving on down here, we have number 1 is a town has a current population of 12,468. The population is growing by 2% per year. Write an exponential equation to model the population growth, and what will be the town's population in 8 years, and what about when will the population first reach 2,000 people, okay? So using that little bit of information there that I just gave you, so here we have what would be our final quantity. Are we given a final quantity? So this one is going to be our unknown, our final quantity. So that one we don't know. How about an initial quantity? Are we given an initial quantity there? Well, actually, if you think about it, the initial quantity is at time 0, so that is the current population. So you know that your initial quantity, I'm just going to label that Q, is equal to 12,468. Then your change factor is basically, if you think about it, it's a rate. So your change factor is equal to 2%. And if we want to do that as a decimal, it's growing by 2%. So that means that we're going to have 100% plus that 2%. So it's going to be 102%. It's growing, because if we only do 2%, it's only do 2% of the entire population. So if we go by 102, it'll be 100% plus that 2%. And changing that into a decimal, we have 1.02. And then the last one here is that we can also find is the number of changes. And are we given that in that question? And if not, then you know what? Let's leave that one. There will be another variable. So now let's put this into that equation that I gave you there, or that general form. So our final quantity, let's label that one, since we are looking at population, let's label that one P. That's equal to your initial, so that's 12,468. Multiply that by your change factor. So multiply that by, and that's as a decimal, so it'd be 1.02. And we don't know the number of changes, and so that one, when we're thinking about that, this is in terms of time. Okay? So this is about all that we're given in the question, so, or at least this is what we have enough to create an equation from this. So from here, we're given two kind of situations. So the first one here is when it says, what will the town's population be in 8 years? That means that T is equal to 8. So putting that into that equation, we have P is equal to 12,468 times 1.02 to the power of 8. Then you guys can put this entire thing into your calculator. So put 12,468 times 1.02 to the power of 8. Put all that into your calculator. What you guys should get is that P is approximately equal to, and we're going to round to the nearest person. We don't want half of a person. So that we have approximately equal to 14,608. So after approximately 8 years, it will change. Our population will become 14,608. Okay. For part 2 of that question there, number 2, we have, when will the population first reach 20,000? So that there is your final quantity. So they want to know what happens when P is equal to 20,000. So you're going to plug that into your equation. We have 20,000 is equal to 12,468 468 times 1.02 to the power of t. So from here, we're given the only variable that we have here is t, so we want to isolate t. So first what we're going to do is we're going to divide both sides by 12,468, so we can get this term by itself. So we have 20,000, divide that by 12,468, and that is equal to 1.02 to the power of t. Just going to scroll on down here so that way I have some more room. I'm a sloppy writer with my writing pad, so hopefully you guys still have some more room. Alright, so from there what we're going to do is we're going to use those statements that we know. So we're going to write each side as a logarithm. So we have the log of 20,000, divide that by 12,468 is equal to the log of 1.02 to the power of t. Using our power rule, we can move this t out front. So we have the log of 20,000, divide that by 12,468 is equal to t log 1.02. Now this is already starting to look like what we just saw. So what we're going to do here is we're going to divide both sides by the log of 1.02. So we're going to have the log of 20,000, divide that by 12,468, and I'm going to put little brackets around there, then divide that by the log of 1.02. Once again, you guys could put that whole entire thing into your calculator and find a value for t there. And what you guys should find is that t is approximately equal to, and if you guys want to do this in decimals, typically we could write this, it's usually best to do it by whole years. So what you guys should find, it should be 23.86 years, and we can round that to approximately 24 years. Okay? So what they're saying is it'll take approximately 24 years for that population to reach 20,000 there, okay? So that is example number 1 there. Now let's move on to example number 2. So I'm just going to quickly erase this there and start number 2 there, okay? So number 2 here states that a business invests $450,000 in new equipment. For tax purposes, the equipment is considered to depreciate in value by 20% each year. Now we need to write an exponential equation to model the value of the equipment. What will be the value of the equipment in 3 years? And when will the value first drop to 100,000? Okay, so from this we're given a few different things here. So are we given the final quantity here? Are we given that FQ? Sorry, I'm going to use my abbreviations here. And so this one we're not given this one. And how about our initial quantity? Are we given an initial quantity? So that one is actually what we first invested. So we had your initial quantity there is 450,000. Then moving on, so what about the change factor? Do we have a change factor? And this one here, it says it depreciates in value by 20% every year. So that means that it is 0.2%. That is how much it depreciates by. So actually what's going to happen is what we're left with is 80% of that value, or 0.8. So 20% of it depreciated, so what we're left with is 0.8. So that is going to be our change factor. That is what will be left. Okay? And then are we given our number of changes, which, so our number of changes. And this one we're not given yet. We don't need this one to create the equation. So using all this information here, we are going to write, here we're dealing with the value, so that'd be your final quantity. We're dealing with the value of the equipment invested. So say we'll let that be V is equal to, that'd be your initial quantity, so that'd be 450,000 times that by your change factor, 0.08, or sorry, 0.8, and as to the exponent of, we'll say that's t. Okay, we're not given, and we're dealing with time here, so your exponent there will be t. We don't know how many years, so we'll just label that as t. So from there, here's our equation. From there, we're going to use, so our first one here says, what will the value be of the equipment in 3 years? So this one here is talking about your time. So time is equal to 3 years. Okay, so we're going to be looking for our value. So we have 450,000 times it by 0.8 to the power of, and here we're going to substitute in 3. This one's pretty nice here. We can plug that into our calculators. And we should find that V is approximately equal to $230,400. So that is in 3 years. Okay. Number 2 here, I'm just going to write that over here. So when will the value first drop to $100,000? So here we're given our final value. So here the V is equal to $100,000. Substituting that into our equation that we created, so we have 100,000 is equal to 450,000 times 0.8 to the power of t. So here we're going to find our time. And just like we did before, we're going to divide each side by this value here, so we can get 0.8 to the power of t by itself. So divide each side by 450,000, and what we would have is 100,000. Divide that by 450,000 is equal to 0.8 t. And then just like we did before, what we can do is we're going to take the log of each side. So we have the log of, and if you guys want to, we can also simplify this. So when we're dividing, those zeros cancel out. So what we'd have is the log of 10, divide that by 45, is equal to the log of 0.8 t. I'm just going to keep rewriting right there. And then what we can do, just like last time, we're going to move this t by using our power rule. So we have the log of 10, divide that by 45, is equal to t log of 0.8. And then once again, just like last time, we're going to divide each side by log of 0.8. So we have the log of 10 over 45, divide that by the log of 0.8, and that is equal to t. Put that into your calculators, and what do you find, ladies? Here you should find that t is equal to, or it's approximately equal to, yikes, alright, that is approximately equal to 6.7 years, or we could just round that up to 7 years. Alright. And just one note here, we really should write a sentence, so I'm going to quickly erase all this, and we should be writing sentences with all of our word problems. So here what we can say is, so the first question there, so we could say the value of the equipment after 3 years will be, we could say, approximately equal to, and we came up with $230,400. Okay, then you guys are going to do the exact same for the next one. So what you guys are going to say is maybe approximately after 7 years the value of the equipment will be $100,000. And I'm running out of time here, ladies, so I trust that you guys can create those sentences, and then you guys can get started on your homework.